Curves in industrial design. Derivatives of a cubic Bezier curve. The cubic Bezier curve is determined by the four vertices of its control polygon. In general, the time parameter of the curve is taken to line 0 to 1, and the curve has an analytic expression that's a linear combination of the control points with coefficients equal to the polynomials in the Bernstein basis. If we wish to work with a different interval, say u to v, we can transport the cubic Bezier curve to this interval using the transformation that sends t to t minus u divided by v minus u, which maps the interval u, v onto 0, 1. This is a linear map in t. When t equals u, the numerator is u minus u, so equals 0. So u gets sent to 0. When t equals v, the numerator is v minus u, which is equal to the denominator, also v minus u. And so v gets sent to 1. Using this change of variables, the cubic Bezier curve on the intervals u to v has an analytic expression exactly like the analytic expression of the cubic Bezier curve on the interval 0 to 1. The only difference is the arguments of the Bernstein polynomials have changed from t to t minus u divided by v minus u. Now we can use this expression to study the derivative of the cubic Bezier curve. When we take the derivative, the control points are constant in t, so they don't change. When we use the properties of the Bernstein basis, the Bernstein polynomials entering in the expression of the original Bezier curve are cubic. We know that the derivatives of cubic Bernstein basis are quadratic Bernstein polynomials. Using these relations, we can obtain, for the first derivative of the curve, an analytic expression, which exhibits it also as a Bezier curve. It's a linear combination of points which have the following form. They're the differences of points in the control polygon divided by the length of the interval under consideration and multiplied by 3. The coefficients are quadratic Bernstein polynomials evaluated at t minus u divided by v minus u. This exhibits the derivative of the cubic Bezier curve as a quadratic Bezier curve. It's also possible to give a nice geometric interpretation of the derivative of a Bezier curve. Here we see the curve and the control points. We want to understand the meaning of the first term in the expression for the derivative of c as a quadratic Bezier curve. When we take t equal to u, the argument t minus u divided by v minus u is equal to 0, and of the three polynomials in the Bernstein basis of degree 2, two of them vanish at t equals 0, and the other takes the value 1. It follows that c prime at u is equal simply to the coefficient of the first term of its expression as a quadratic Bezier curve. This coefficient is c1 minus c0 rescaled. c1 minus c0 is simply the vector that points in the direction of the segment that runs from 0 to c1. It follows that at c0, the cubic Bezier curve is tangent to the first segment of its control polygon. Exactly the same reasoning taking t equal to v, which corresponds to isolating the last term in the expression of the derivative of the curve as a quadratic Bezier curve, shows that at the final control point, the cubic Bezier curve is tangent to the last segment of its control polygon. So we can summarize by saying that a cubic Bezier curve is tangent to the first and last edges of its control polygon. A similar development is possible for the second derivative. Again, we take the derivative term by term, and we use the fact that the derivatives of the quadratic Bernstein polynomials are linear Bernstein polynomials to express the second derivative of the cubic Bezier curve as a Bezier curve of degree 1. The coefficients now are somewhat more complicated, but again we can give a sort of geometric interpretation to them. Here we see the Bezier curve and its 4 control points. By taking t equal to u, we isolate the first term in the expression of the second derivative of c as a linear Bezier curve. If we work a bit, we can interpret the coefficient that results to see that it's a vector that points in the direction indicated in the drawing. So we consider the first two segments of the control polygon. They form a sort of triangle, and we find the direction which splits this triangle. This is the direction of the second derivative of c at u. Similar reasoning applies, of course, to t equal to v.